So I have received your good afternoon, Joshua. I have received your marks, and overall, I am a bit happy because the performance is increased in comparison to your first internals. I am not sure whether you have an open book system for your attempting the questions, but anyway, I trust you people, thinking that you have done everything from your mind and the answers and most of the questions, as I already told you, will have different difficulty levels, and the questions and the answers, whatever you have done, are taken mostly from outside, right? I don't think you will find that in internet or maybe somewhere. So if you have taken a good mark, that really shows that you have learned something in machine learning. That's what I want to test. So I'm a bit happy with that because overall the marks are on the higher side. But interestingly, nobody has got the complete 40 out of 40 so far. You can check your marks. I have entered that. I think 37 is the 37 point something is the maximum one. Maybe next time you will go. You can go for the complete 40 out of 40 also. But still, two of you have failed. Less than 20, you have scored less than 20, which again is not a good sign. See, always remember that when I look at you people, right? For me, the class is important. For me, the class is important. So when I find that, okay, among 70, 68 passed, and okay, then I'll be happy and then I will leave away. But for you individually, those two people who failed, it is the problem for you, only for you. So you need to come forward, get clarified your doubts, learn more, and then try to get at least more than 20. That's the way how we have to learn, not more than 20, something closer to 30 or 35 will be ideal. But if you can't, you can at least try to go for something beyond 20 also. So that is my observation from your performance, and still I'm expecting more when we go for our third interview. Because I took everything in a different way. The questions are framed in a different way. I think that you would have got some information about machine learning. You would have not have found these questions in the internet or in the PPTs or in any books also. If you have understood the class, then mostly you would be able to give that answer. So today is the last topic of our fourth unit, support vector machine. So as we saw, if we take a recap of what we have learned in the previous four chapters, you can see that first chapter is all about introduction on machine learning techniques, and second chapter talks about the classification and the regression part. That means you must know what is meant by classification, what is meant by regression. And when you go for your third unit and the fourth unit, we saw about two algorithms or two widely used machine learning techniques. One is called as the decision tree and the other one is called as the support vector machine. Decision tree and support vector machine look almost same, except for a small difference that decision tree is normally used for different types of classification, and sometimes it is also used for regression applications. Right? Mostly we go for regression. CART is mostly used for regression, but we can use it for classification also. But when you go for support vector machine, it is more preferred for classification than your regression. But both the techniques can be used for both the applications. Right? Decision tree is all about curve fitting, trying to fit all the points during your training process. But your support vector machine is all about finding the margin or the distance between the 2 points or the two from the different classes. Maximizing that will give you the better answer. So now we go into another small topic for today's session. Let me share my screen. This already we learned, right? Just a minute, I will download that and I will let you. 1 minute. Is my screen visible?
Yes, sir.
So today we are going to see something about an algorithm which is called as sequential minimal optimization algorithm. Right. So we saw that our SVM purpose is to find out the hyperplane which has a maximum distance. So in connection with that, we had an equation. Right. We had an equation both in the primal form and also in the dual form. We had an equation and we were trying to find out some parameters, A, B, C, or the W values. So what should be the optimal values of those parameters? If you can find the optimal values of those parameters, then you can fit into that specific equation. Then you can find a hyperplane which is going to give you the maximum margin distance. So if you look at this algorithm is a common algorithm which can be used for any optimization applications. But when it comes to support vector machine, we are making use of this SMO algorithm to find the parameters to find out the optimal hyperplane. So it is more into a mathematical part, right? But I'm going to just trunk everything to the specific need of you people, right? All those specific mathematics is not that much important. Generally, you can have a rough idea on how this SMO or sequential minimal optimization is going to be used for this. As you can see, SMO is an algorithm for solving the quadratic programming. So quadratic programming, whenever you have an equation, you are going to have powers 2, power 3, power 4. All such type of problems are called as QP problem in mathematics. So those can be solved with the help of SMO. And specifically, because your SVM has such equations, SMO is widely used. It is invented only in the year 1998. So after the release of SMO algorithm, people were much attracted towards algorithm, and those specifically working in SVM based algorithms or SVM based regression and classification applications, they use this SMO much than other optimization algorithms. Right? So they say that this SMO is relatively less complex and require less memory requirement for the hardware implementation. Right? But for us, we are not mathematicians. We are much into the machine learning algorithm part. Right? As for us, even that method seems to be a bit more complex. But anyway, getting some idea on those things is not at all a bad idea. So consider a binary classification problem with a data set x1, y1, xn, yn. Right? So you have an input data set and you have also a target. You also have a target. Right? Now the second bullet point says a soft margin support vector machine will have an expression of this sort, right, in the dual form. This dual form which we have already seen. So now my purpose is, or my objective is, to maximize this equation. To maximize this equation, or specifically, I need to find alpha. I need to find what should be the correct value of alpha. So when I get that correct value of alpha, if I substitute here, this equation is going to give me the highest possible value or the maximum value. And that alpha has some constraints, which we say that it falls between 0 and a constant, where constant C is a hyperparameter. Right? You can fix. Whenever alpha changes, this C will be your alpha changes, but your alpha should be within this range of 0 and C. So SMO is an iterative algorithm for solving the optimization problem or to solve that specific equation. So how it is going to handle this equation? It is going to break this problem into a series of smaller equations. Right? This equation seems to be a bit large. Right? You have two terms, and even within these two terms, you have many summations. So our SMO algorithm is going to break this equation into small pieces, and then each piece is going to be solved analytically. And we already saw an expression represented in the dual form is also called as Lagrange equation or Lagrange multiplier. So each small equation or each small part of the equation can be called as a Lagrange multiplier. Right? So if you have alpha 1 and alpha 2, when you will have alpha 1 and alpha 2, when I is equal to 1, j is equal to 1. Suppose if I and j value increases, right? If the number of classes, binary classification, okay, alpha 1, alpha 2. But if there are more number of classes, the number of alphas also will change or it will increase. So the problem will become more complex, that you will be asked to find more optimal values of alpha and alpha 1, alpha 2, alpha 3, and so this is a small algorithm how the SMO works. Step number 1, 2, and 3, and you randomly choose alpha 1. Right? You randomly choose alpha 1 based on some KKT condition. I am not sure whether you would have come across this conditions. Right? There are Jacobian conditions, Tucker conditions. Right? These are a bit higher level mathematical concepts which revolves around optimization problem. Right? You need not worry about it. The concept is choose a random value of alpha 1, and with the random value of alpha 1, you try to estimate alpha 2. Then with that alpha 2 value, again you are going to change alpha 1. And this process will keep on continuing till this KKT condition is satisfied. We have a convergence condition, and when it satisfies, we can say that is the correct value of alpha 1 and alpha 2. So when you execute your SVM algorithm, this optimization part is just maybe 10% or 15% of your complete SVM process. So it will be automatically executed and you will get a correct value of alpha 1 and alpha 2. Once you get that, you have to come back, substitute here, and check whether this equation is maximum or not. If this equation is not maximum, again that specific SMO part will be executed, and this process will keep on continuing till you get the maximum possible value for a specific equation. After that, your alpha 1, alpha 2 value will not change. When it doesn't change, you can come to a conclusion that, okay, this is the maximum possible value I can get for this specific alpha 1. So you need not go into the mathematical part of this, but for the time being, you can understand that this SMO is an optimization algorithm which is used to find the best possible Lagrange multipliers in the dual form of SVM equation. When do we use dual? Only when the data is nonlinear or complex. If you have a simple data, this SMO algorithm will not have any work in your specific method. But normally 99% of the time, your data will be complex and nonlinear. So we go for the dual form. Whenever you go for dual form, you will get the Lagrange multiplier, and that Lagrange multiplier values has to be determined. If those values are not determined, then you will not be able to get the correct hyperplane equation. How do you determine? Using this SMO. So if you ask for the programming part, or when you go for implementation, you need not go for SMO separately because it is inbuilt within SVM. Let me show you a small blog on how your implementation part of SVM can be done. Can you see my screen? I'm not sure whether my screen is visible to you.
Yes, sir.
This is the SVM part. Most of the stuffs which we have already seen. I just want to bring your attention to the implementation or the coding part. So what's an algorithm? What is an SVM? How an SVM works? Linear SVM. All these things we saw. This is a linear SVM. And this is a non-linear SVM. How we can go for that types of SVM. Simple SVM for a linear data, kernel, all these things we saw. Some advantages, some drawbacks, which also we saw. These are the different kernel functions. The equations I gave you in the previous class. So now we will see a small implementation of SVM with Python language, right? I do not know Python. You need not know Python. Just know the procedure of how we go for implementation in SVM. I would just want to inform you that with the advancement of software technologies, the implementation part is very, very easy. Very, very easy. But if you implement that without any background idea of SVM, you will not be able to build upon what you have already implemented. No new innovations, no difference between you and your peer group will be there. Right? So when you can have a background idea on what is happening along with your programming part or implementation part, then it will be much more easy. So the procedure is very simple. You need to have the data set, right? You need to have the data set and explore the data to figure out what they look like, whether they are linear or whether they are non-linear. Right? If they are non-linear, you will have some additional work to convert into a linear form with the help of your kernels. Right? Then you need to have your attributes and labels. As we saw earlier, SVM also come under the category of supervised learning for classification. So when I say blue color data and a red color box, blue color maybe class 1, box class 2, that you need to specify. Then as usual, we are going to divide into training and testing and train the SVM algorithm, right? The sixth point is the one for which we have spent all the previous 4 or 5 classes. But interestingly, when you look at the programming Python language, it is only a single line. It is only a single line with which you can go for train your complete SVM algorithm. But I would advise you, why can't you make some new inbuilt commands even in Python language? They would have used some .fit command. Right? .fit command, if you right click and check, they will have many inbuilt functions and source codes within that. It is given as a cake to you. Now, how you can prepare a cake and give to the outside world? For that, you need to have all the background information of SVM. You may learn all these things and you will get some idea on where some changes can be made. If I make a change in this algorithm in this part, then how my system will perform or how my application will perform. That will be the main duty of a machine learning engineer, right? It is not that taking some data set, taking some inbuilt code, run the program and showing the output. What changes you can make, right? That is the purpose of myself again spending all the 5 to 6 classes in this specific supported dimension. And again, we go for predictions and we go for evaluation. Right? So the process seems to be very simple. So when you go for Python, these are the some of the inbuilt APIs which you need to have in the beginning to make sure some of the libraries or the commands which we are going to use will function. Right? I hope you must be knowing that, because some programs we did already in Python in the previous semester, at least in the DSP lab, I think. Then you have your data. So here you have a linear data. So you need not worry about the kernels. Right? You need not worry about the kernels. You have a capital X and you have a capital small y. So when you plot that, you will get a sufficiently different concepts of X and Y. So some data will be on one side, some data will be on other side. So you can easily divide, right? So this graph, this point, this is nothing but the pictorial representation of our NP array capital X and small y. Right? So if I want to divide these points, I can draw a line here, I can draw somewhere here, and I can say my data is classified. So how do I do that? If you want to have some arrangement of data, you can have some arrangements. And as I told you, this is a bi-level classification. SVM can be used for multi-level, but what we have seen so far is bi-level, and you can give a target as 0 or 1. Now we can create a SVM model using a linear kernel. What do you mean linear kernel? It is a normal process. It is a normal process. Right? So this command, svm.svc, creates your complete SVM. Whatever we have seen, it will create a complete SVM, and it will also know or have an idea that your hyperplane is going to be a line, because it is going to be a linear data. It is going to be a linear data. So for that equation of that line, to find that parameters, unknown parameters in this line, we go for optimization. Right? So as we have seen in the previous, we will give this capital C as 1, because your alpha or the Lagrange multipliers are going to be between your 0 and 1 value. So dot SPC creates your model, and this command, right, this one line of code completely execute your program, right? Or in other words, it is going to check for different possibilities of alpha. This, whenever we train, we get different values of alpha. We go and fit it in our equation, and we will get a line and check how our line works, whether it is good or not. Right? If not, again our alpha is changed, and this process will keep on continuing. Right? So dot fit command is used for your training the complete process X and Y. So from that training process, you can get all the outputs. You can get the coefficients. Right? These are all the output. What are the outputs you can get? You can get the coefficients. What are the coefficients? Do you remember our expression? Y is equal to W transpose X, where W is a vector, X is a vector. If it is a 2-dimension, you will have A, B, 1. So that A, B values you can get. W is a vector, which in turn has A and B. You look at the first PowerPoint which I have uploaded. So that from there you can get that A and B. And we can also get the first iteration, the second iteration, change parameters. Then you can have the intercept. You can find the intercept of the equation. So when I say the output is a hyperplane or a line, it is not actually a line. It is the equation of the line. That means in turn it is the parameters of that equation which will be the output for your process. Okay. Then you will get a line which is going to divide your data. Okay. So just take the data, go for some pre-processing if necessary. Then you use your .svc command, where it is going to create your SVM based on the data and the target values. Then we go for just .fit, which is going to create, train your complete model. Non-linear. In the same way, we can also go for non-linear. These are again some application programming interface. We call it as APIs, which can be used for some libraries which you are going to include there. You make your own data. Here we have a non-linear data, 300 samples in the form of a circle. And this is what I showed you or displayed you long back, right? Maybe the previous week when we saw about the non-linear SVM. So I am creating my own data. I am creating my own data to show you that yellow color and purple color are. fixed. So now I need to go for a kernel. Without a kernel, I cannot go. If it is linear SVM, I went for a linear kernel. Right? Linear means your normal y is equal to mx plus c. But here I go for RBF kernel. Right? Again, I'm specifying the value of c because I know the alpha values lies between 0 and 1. So based on this kernel, my output changes. My output will change. Again, you go for your training where we again go for dot fit. Okay. Dot SVC is used for creating the SVM model, and for training your SVM model, we go for dot fit. All the previous contents which we saw in the 5-day session is within these two equations or two Python program. So only if you know internally what is happening, then you can create some kernel on your own, and you can argue with MathWorks. MathWorks are looking for engineers. MathWorks, you know, it is the source for MATLAB. Right? In the same way, Python also has a specific controlling office. Those people are looking for machine learning engineers to give them an inbuilt code, like our .svc, like our .fit. So you can develop an algorithm, you can make it in the form of a code, and then you can even sell to MathWorks. That is called as software products. So whenever people talk about products, don't think should be something visible to our eyes. That is fine. But there are also software products which are on demand for people like machine learning, people working with machine learning or data science. So .fit, now if you see, you can get the same results. But the only thing what you will have when you go for nonlinear SVM is you are going to represent in a 3D way. Right? So you need to go for the mesh grid option and different options to check whether how your stuff works. Now you can see that it is differentiated. Your purple color and yellow color are differentiated. So that is with the help of your RBF kernel. In the same way, you can have your own other kernels also. So this is what interesting. I just want you people to read, right? This person, this blogger, right? He is writing that you might wonder, you means we might wonder why I didn't go into the deep details of the math here, right? So whenever you talk about machine learning, you should know your position first, whether you are a mathematician or whether you are a machine learning algorithm developer. If you are in an algorithm developer mode, then more amount of mathematics is not necessary. But if you really feel that I want to find the inner details and make some changes, then you can straight away learn maths also. But as a faculty, as a person who is guiding you, I do not know which mode you are in. That's why I have the mixture of both mathematics and the algorithm part. But now the choice is yours. Now the choice is yours. Some of my BE classmates are now working in Cisco and some other deep learning companies. Right? So whenever I have an interaction with them, they used to say that, Jude, just have the deep learning modules and then everything will work. But who is there to create the deep learning models for them or modules for them? It is machine learning engineers like you people. Right? There are many algorithm developers working in this area. Algorithm developers are high demand for this machine learning industry. So try to have some interest on that, try to go deep into that, and then you can produce some good output. This person who wrote this blog, he is a machine learning engineer, or I can say that an advanced programmer who is viewing this from a computer science point of view. Right? But if you can have a bit of maths, then it will be good too. It's mainly because I don't want to scare people. Right? This line is interesting. It's mainly because I don't want to scare people away from learning more about machine learning. So all the equations, they need some higher level of mathematics. It is fun to learn about these long, complicated math equations and the derivations, but it's rare. Right? This is what is important, but it's rare you will be writing your own algorithms on real projects. That how much you are going to use this SMO algorithm, it is available. SMO algorithm, it is available. So if you want to make some changes, you need to work on other optimization algorithms. Again, writing a code for SMO may not be necessary. Again, putting your hands in the mathematical equations of SMO may not be necessary. Right? So when you are learning machine learning, some people may look it from a mathematical point of view. Sometimes it may be from a computer science programming point of view, and some people may be from the algorithm point of view. And as you come under ECE category, I advise you to view it from an algorithmic point of view, where a bit of mathematics, a bit of programming is more than enough for you to develop some good machine learning. Okay. Machine learning is like any other software engineering application where you can find plenty of concepts or contents available everywhere. Right? So this is just one example. Likewise, there are so many examples available in the internet where you can explore further. Try to have these codes in Python, or if you are comfortable with MATLAB, that is also fine. Try to find those, implement and check how all the theoretical concepts which we have learned so far can be put into real time. So with this, your support vector machine is over. I am very sure that with this idea, if you explore further, you can do some very good projects with the help of support vector. Let me mark the attendance. Amulya. Amulya.
Yes, sir.
Jetson.
Yes, sir.
Samyukta. Samyukta not there. Okay. Angel.
Present, sir.
Ajit Pawan.
Present, sir.
Abhinaya.
Yes, sir.
Kiran Kumar. Kiran Kumar.
Chat box, sir.
Manideep. Okay, Manideep. Chat box. Manideep absent. Banu Teja.
Present, sir.
Jennifer.
Yes, sir.
Priyadarshini.
Yes, sir.
Jeevan.
Present, sir.
Afreed.
Present, sir.
Jayant. Jayant. Jayant absent. Okay. Vikas. Paul Finney.
Present, sir.
Bhuvaneshwar.
Present, sir.
Sumant Kumar.
Present, sir.
Ramesh Kumar.
Present, sir.
Neeraj Kumar.
Yes, sir.
Zubair.
Yes, sir.
Kirti.
Yes, sir.
Dinesh.
Yes, sir.
Tejaswant.
Yes, sir.
Chandana Priya. Chandana Priya absent. Karthik.
Yes, sir.
Vijay Kumar.
Sir.
Soman.
Yes, sir.
Janish.
Present, sir.
Rex Vimal. Rex Vimal. Absent. Harshavardhan.
Yes, sir.
Uday. Sakib.
Present, sir.
Siddharth.
Yes, sir.
Praneeth. Praneeth.
Sir, chat box.
Okay. Salome.
Yes, sir.
I think Salome and Suraj, they scored the maximum, I think. 37 point something. Good. Livingston.
Yes, sir.
Alan.
Yes, sir.
Joshua. Joshua. Ronan Joshua. Okay. Sai Kiran,
Yes, sir.
Joshiba,
Yes, sir.
Shiny,
Yes, sir.
Jasmine,
Yes, sir.
Kavya,
Yes, sir.
Jayasurya,
Yes, sir.
Jonah Paul, Manasa, absent. Okay, Manasa absent. Ashrita,
Present, sir.
Narasimha Reddy,
Yes, sir.
Puneet Kumar,
Yes, sir.
Shiny Rebecca,
Yes, sir.
Joshua,
Yes, sir.
Nagakiran,
Yes, sir.
Suraj,
Yes, sir.
Maunika, Taufik,
Yes, sir.
Sai Manideep,
Present, sir.
Dikshit,
Yes, sir.
Maria Angel,
Yes, sir.
absent. Angel, okay. Amrut,
Yes, sir.
Pavan Kalyan,
Yes, sir.
Sainath,
Present, sir.
Gautam,
Sir, present, sir.
Jagat Chandra,
Present, sir.
Vivekananda,
Yes, sir.
Shashan,
Yes, sir.
Sai Ganesh,
Yes, sir. Yes, sir.
Okay. Gopichand,
Box.
Ritvik, thanks, Pa. Ritvik absent. Okay. Solomon,
Present, sir. Ritik, sir.
Yes, sir.
Solomon,
Yes, sir. Present, sir.
okay. Sudarshan, absent. Sujit Kumar,
Yes, sir.
Suresh Kumar,
Yes, sir.
Sunny,
Present, sir.
Amrita Das.
Present, sir.
So the absent is number 7, number 36,
Sir, 7%, sir.
7 present.
Yes, sir.
Judson present,
Yes, sir.
not Judson, sorry, not 7. You are 7, Manideep,
Yes, sir. Yes, sir. He texted in chat, sir.
chat box.
Yes, sir.
Number 36, Chandana Priya absent, then 41, Rex Vimal absent, then 71, Manasa absent, then 135, Sudarshan absent. So next class onwards, we will go into another machine learning techniques, which is called as artificial neural networks. And if you ask me, artificial neural networks and then its advancement, deep learning, right? These are the two things which are being used widely now in comparison to SBM and decision trees. So when you completely study all these concepts, it will be like you are having a good idea on machine learning techniques. Thank you, students. We will meet in the next class.